Good evening everyone. In this video I will be discussing about reliable multicast and the algorithms using which you can actually achieve reliable multicast. We'll be looking at the system model, okay, and then we'll be looking at the holdback queue, what it is, okay, and then we'll try to see what is basic multicast, and then we'll try to see what is reliable multicast over this basic multicast, whatever we will be seeing, okay, and then we will also see reliable multicast which can be based on IP multicast. So the system under consideration basically contains a collection of processes which actually can communicate reliably over one-to-one channels. So that means they can have this sort of reliable communication one-to-one between two processes. The term reliable actually in this one-to-one communication is actually defined in terms of two terms. One is validity and the one is integrity. So the validity actually means any message in the ongoing message buffer is eventually delivered to the incoming message buffer. So that means if there is a process 1 and process 2, P1 and P2, okay, if a message is basically put into this sort of outgoing message buffer of P1, that means it will eventually be delivered into the incoming message buffer of P2. This we can actually achieve by using this sort of acknowledgements and then retries. Okay, so this is how even TCP basically sends the message at the transport layer. Okay, so the same thing at application layer we can actually achieve it with this sort of one-to-one communication. Okay, that's about validity. You can also achieve integrity. So the message actually received is identical to the one which is actually sent. Okay, so that means no tampering has happened with the message. Okay, that is one thing. And then no messages are actually delivered twice. So if a message is already received, you need to be able to drop it. Okay, so that means you are actually rejecting the duplicates, and duplicates most often will be coming because of multiple tries. Okay, so you will be retrained so that if the message should be actually reached. Okay, because this one-to-one communication is a reliable communication in this case. Of course, if you want to maintain this sort of there is no tampering of the message, then you can actually use the checksums. Okay, and one more thing is as far as this type of system is concerned, processes may fail only by crashing. Okay, there is no other way. Okay, so if a machine crashes, okay, if a process crashes, then it's okay, it is agreeable. Okay, whereas it should not be tweaking or tricking anything with the acknowledgement or something like that one. If a process basically crashes, means it is for that particular time it has actually failed. The processes are actually members of the groups, okay, which are actually the destination of the message, and then these messages are actually sent through this sort of multicast operation. Okay, this we have already seen. In general, process P can actually belong to more than one. Okay, so the process can participate in multiple groups at the same time actually. But then the operation multicast Z comma M. Okay, so in this case it is the group to which the message is actually sent. Okay, so once you basically call this method, okay, that will actually send the message M to all the members of that particular group, okay, who are actually registered to that particular group. Okay, group G in this case. And then there is another very interesting method here, deliver of M. Okay, deliver the messages. So this actually delivers a message sent by a multicast to the calling process. This deliver message is actually different from the receive message. So once a process immediately receives the message, it is not immediately sent to the process. Okay, so that at the application layer, so that it can actually process the message. Sometimes you may actually have to delay that particular message. Okay, say for example, if you want to achieve ordering or reliability or something like that one, you may have to keep that message, okay, and you may have to basically delay that one. Okay, okay, we will be seeing in one of the algorithm, especially for the reliability, how you actually need to delay the message so that you can actually deliver, you can actually achieve the reliability. So for these sort of things, we will be using this sort of holdback queue. So once this message is actually received, the message is actually put in this sort of holdback queue, and when this sort of delivery guarantees are actually met, okay, reliability or ordering or everything is met, then you will actually move that particular message to the delivery queue, and eventually that is the one which is actually delivered for the message processing. This is all actually happening at the receiving process end. Actually, you have to clearly see that one. So that means the message which is actually received immediately is not sent for processing. Okay, this is the way you will actually achieve this sort of reliability or the ordering. Okay, in this video we'll be seeing the reliability in detail. In the next videos, like we'll be seeing the R rate. So in terms of the system model is concerned, every message M actually carries the unique identifier of the sender. Okay, the sender process which actually has sent that message. You can actually get it from using this method, sender of M. Okay, and it can also have you can also extract the destination group to which like that particular message is actually sent. You can get that information using this sort of group of M. And another very big assumption in this case is like we assume that processes do not lie about the origin or destinations of the messages. Okay, that is another very important thing. So now let us look at this sort of basic multicast. The basic multicast primitive actually guarantees that a correct process. So the processes which actually never fail, okay, these processes will eventually deliver the message as long as the multicaster does not crash. Say for example, if P1 is the multicaster which is actually sending to all the other processes. Say for example, whatever this basic multicast basically guarantees that as long as these processes, okay, are correct, okay, the message will be eventually delivered to those particular processes. Okay, of course, if the multicaster itself, the process P1 itself fails, that's a different ballgame completely. But remember this one, this is the thing, like this sort of primitive is not guaranteed by the IP multicast. The basic IP multicast says like it will try its level best, okay, it will give its best effort to say basically send the message. But of course, like some of the processes in that particular multicast group may not receive the message. Whereas this basic multicast, okay, which we are talking about in the form, like I will actually define the algorithm for that one, okay, B multicast. This will basically ensure that eventually the message is actually delivered to all the processes as long as the multicaster does not crash. The one which is actually, which originally sent the multicast message does not crash. We call this primitive B multicast as I already mentioned, and its corresponding basic delivery primitive B deliver. Remember that one, it is not receive, it is actually deliver. So you received it, you put it in the holdback queue, okay, and then like you will deliver it when it actually meets everything. So this B deliver is about the delivering the message to the process for processing that particular message. If you want to have a simple and straightforward method for that one, of course, like it is ineffective in terms of the implementation is concerned, we can actually use this sort of one-to-one reliable send. Okay, we already have discussed in the system model that there is a way you can actually send like one-to-one messages reliably. Okay, using that one, like when you are trying to be multicast this message to that particular group, what you will be doing is like for each process within that particular group, P actually belongs to G, send P comma M. So that means like for all the processes which are there, okay, send that message to that particular process. Okay, so this is one-to-one reliable communication. And at the receiving end, okay, at the receiving process, once you actually receive the message, okay, at particular process P, you will actually B deliver message at particular P. So that means like once you receive the message, okay, you kept in that particular holdback queue, and eventually you are actually be delivering that message to that particular process. In this case, it is P. So then what you are doing is like in simple terms, you have the multicaster from which like you are establishing this one-to-one connection to all the processes, and you are actually sending that message using that reliable one-to-one connection, and there at this sort of receiving process you will actually be deliver that message for actual processing. But the problem with this particular basic multicast is if the number of processes is really large, the protocol will actually suffer from hack implosion. So the basic idea is to achieve this sort of reliable multicast, you need to basically have some sort of acknowledgement, isn't it? You send the message, you basically acknowledge that the message is actually received. So the receiving process basically has to send that one. That is how like you will be achieving this reliable one-to-one connection. In this case, what happens is like if there are a lot of processes, so that means like this multicaster individually is sending to all the different processes, then it will basically receive all the acknowledgements. Okay, so if it is receiving a lot of the acknowledgements at the same time, some of the acknowledgements may be lost because like the buffers are actually full. That in turn like actually states like for the process 1 which actually has multicasted all the messages, since the acknowledgement is lost, so it thinks like the message is not delivered. So that means like it will try to re-deliver the message. So if it re-delivers the message, then more acknowledgements. So this is actually called this sort of ACK implosion. Okay, because of that one, this basic multicast. Okay, so the algorithm in the way like I have defined this one is a really a bad choice. So now let us look at reliable multicast. So that's about the basic multicast. This reliable multicast, the protocol is correct even if the multicaster, which actually pushed that message to that particular group, multicast that message to the group, even that node crashes, still the protocol should be correct. Okay. So then to achieve that one, it actually has to support three criteria. One is validity, another one is integrity, and then like the third one is the agreement. Basically, the integrity means like a correct process P delivers M at most once. Remember that one, it is not receiving. A process P delivers that particular message at most once. Okay, to the application which is actually processing that particular message. Okay, so with the integrity, a process okay delivers message at most once. In this case, like the P actually belongs to that particular group. Okay, so that is when like it is actually trying to deliver that particular message. Okay, and the M was supplied to this sort of multicast. Okay, so using this particular operation like sender M of M. Okay, so that means like you are actually sending that particular message. So that's about the integrity. So a correct process basically will deliver that message at most once. Then the validity basically says like if a correct process basically multicasts M, okay, it will eventually deliver M. So remember that one. If a process is actually multicasting, okay, a particular message, eventually even that one is also receiving that particular message. If process P is sending message M, I mean if it is multicasting the message M, eventually even process P will also receive that particular message and it eventually has to deliver it for processing. So that means like if a correct process multicasts M, it will eventually deliver M. Okay. So that is basically about validity. Integrity, you are sending the message at most once, okay, up. And then like validity basically says like if you are multicasting, then you are also receiving that particular message and you are actually delivering it. Okay, that's about integrity and validity. And the third one, which is actually very interesting, is this agreement. If a correct process actually delivers M, then all correct processes in the group will eventually deliver M. Remember that one. So if one of the processes, okay, actually delivers a message M, then all the processes within that particular multicast group, okay, will eventually deliver M. Okay, but remember this one. This is not a property which B multicast algorithm is actually guaranteeing you that. But this reliable multicast actually has to basically guarantee you that. Interestingly, if you are basically saying like validity and then like agreement both are ensured, okay, that means like it basically states like that particular process is live. Okay, so the validity and agreement together amount to an overall liveliness requirement. Okay, so that means like the process is still running because like it has to basically deliver. If it has a multicast, then eventually it has to deliver it. So that means like it is still alive until it actually has received. And then like if one of the node has actually delivered that particular message M, okay, that means like every other process is also delivering that particular message M. So until that multicast is completed, this node is still alive. Okay, so that basically guarantees this sort of liveness. Okay, so that means like it is actually required that the node is actually live always. Of course, like it also provides these operations R multicast and R deliver. Now let us try to look at this sort of reliable multicast algorithm or the basic multicast which we have already discussed about. Okay. Of course, like as I have already mentioned, processes can actually belong to several closed groups. Closed groups are like the basic idea is like the number of participating processes, okay, the processes which actually join the group is actually closed. That means like no new nodes, no new processes are jumping into that particular multicast group. So how you will basically do is like on the initialization, whatever the received message is, okay, that set will be empty. If a process P basically is trying to R multicast a message M to that particular group, okay, the process P is here, it has to send to everyone and it basically has to send this sort of reliable multicast. What it basically has to do is like, it first has to do this sort of B multicast. The basic multicast which we have discussed, the algorithm before, it basically has to put that B multicast algorithm to that particular group G and it basically has to send that particular message. Remember that one. So since P actually belongs to G, it is also included as a destination for this particular B multicast message. So if P has to R multicast the message to that particular group, it has to B multicast that particular message to that particular group. Eventually, using the B multicast, even this process P also has to receive the message. And now, once basically like the B multicast has to deliver the message, okay, eventually like you will receive it and then like you will put it in the holdback queue and then like eventually you will basically B deliver it. When you are doing this sort of B delivery, okay, at a particular process queue, say for example at process queue, if you are B delivering it, okay, where like okay, so the group is where like group of message M, okay, so for all that particular processes in that particular group, okay, so and queue is within that particular group, okay. A particular process Q, if M is not already received, if M does not belong to received, okay, if M does not belong to received, then what you are doing is like into that particular received set, like you are actually putting this message M. So received is received union M. And interestingly, if Q is not equal to P, so that means like if process, okay, if Q is not equal to P. So that means like P is the one which actually has done this particular multicast. Okay. And if this process which actually has received this message, so that means like it is B delivering that particular message. Okay. If it is not equal to P, then you will be actually, this process Q will also do this sort of B multicast again. B multicast that particular message to that particular group, okay, the message again. Okay, and then like once it is actually done, you basically will R deliver the M, okay, reliable deliver that particular M. And if eventually like since that the B multicast is also receiving for the multicaster, so the one process which actually tried to multicast that particular message, okay, if that is the one which is actually receiving that particular message, then it will not do anything, it will not be multicast again, okay. So that's about the interesting thing here. Okay, of course, like you will R deliver that particular M, and that's where like your loop basically ends. Now here, you basically have this sort of two primitives. R multicast is here, okay, and R deliver is also here. Now, interesting thing is to R multicast a message, what this algorithm is doing is a process basically B multicast into the processes in that particular group, including itself. So if a process B is R multicasting a message, okay, that process basically B multicast, that is basic multicast, the algorithm which we have discussed, to all the processes in the group, including to itself. So when the message is actually B delivered, the recipient B multicast into that particular group. So that's what we are actually doing. So if it is different from the process which actually has sent, okay, so if it is not already received and then like when it is basically trying to do this sort of B deliver, okay, it will basically be multicast into the complete group. And see here, if it is already received, the duplicates are already detected and then like you will ignore the duplicates. So by having this particular algorithm, the validity is actually ensured. A correct process will be delivered to itself, that is actually guaranteed, okay. B when you are actually B delivering it, okay, so then only like you will be R delivering it eventually. So the integrity is also ensured because like it is based on this sort of reliable one-to-one channels and you are actually using this sort of B multicast. This actually guarantees the integrity for this particular algorithm as well. Of course, agreement is also guaranteed. Every correct process B multicasts the message to the others. Okay. So if P does not R deliver, that means like it actually has not B delivered, okay? And this happens only because nobody else has actually delivered that one. None of the others B delivered that particular message, okay? So the agreement is also ensured with this particular algorithm. But what about its performance? So each time, like to basically do this sort of R multicast, you are actually doing this sort of B multicast to every other process, and every process when it is actually receiving that particular message, it is again doing this sort of B multicast. Of course, like when it receives the basically the duplicates, it will basically drop it. So the number of multicasts which are actually sent within that particular group is of the cardinality of G. So as many number of processes are there, those many multicasts are actually happening. It will be highly inefficient in terms of performance is concerned. Then the other question is like, is this algorithm correct in an asynchronous system? In fact, actually this algorithm works perfectly in asynchronous system. We have not talked about timeline anywhere. Okay, so that means like it will be, the message will be eventually delivered. Okay, there are no guarantees like when the message will be delivered. Now let us try to look at another algorithm. Here we will try to do look at this sort of reliable multicast over the IP multicast, not the or the basic multicast, the algorithm which we have already seen. Okay, with this reliable multicast, again like as a distributed algorithm, like it will have its own assumptions. Okay, it basically uses this sort of piggybacked acknowledgement messages. See, whenever you have this sort of reliable communication, okay, so you basically will send a message and you will basically get the acknowledgement. Okay, so instead of having a lot of acknowledgements, what this basically approach does is like it will basically have this sort of piggybacked acknowledgement messages. So what it will do is like whenever it is time to send the next message, it will add some additional information to that particular message. So that actually tells everyone that whether that particular message is received or like what is the current state or like which of the message is currently being sent. Okay, by the sending process. Okay, by the sending process, we have to remember that one. And it also uses this sort of native acknowledgements when messages are actually missed. So if any process basically notices that a particular message is actually missed for that particular process, it will basically send this sort of negative acknowledgements either to the sending process. Okay, so if it knows like certain message has not been received from, say for example, P3 or something, okay, it will try to send negative acknowledgement to P3. Can you please send me that message again? Okay, so these are the two things which are very critical for this particular algorithm. So in this case, like basically a process actually maintains, so this sort of sequence number SPG. Okay, so this is a message sequence number for each group it actually belongs to. So that means like the sequence number of the message that it has actually sent to that particular group. Say for example, it has already sent like 3 or 4 messages. Okay, 4 messages for example. This SPG value will be 4. Okay, for that particular piece, process P. It will also have this sort of R. Okay, again this is the sequence number. Okay, this is the sender number, and then like in this case like it is the receiver number. Okay, sequence number of the latest message received from process Q to particular group. See this RQG. So this Q is the one of the process from which like, okay, what is the last message which it has actually received. Okay, it's sequence number, it will basically save. So that means like say for example from process Q, if it has received message 1 and then like message 2 and later like message 3, then RQG will be 3 because like the last message which has received is with the sequence number 3. These two things like actually a process maintains actually. And see this one. So this is only one value, but this is for each and every process within that particular group G. So for a process to basically P to basically R multicast message M to the particular group, what it basically will do is like it will basically piggyback, okay, this SPG value, okay, and it will also add this sort of positive X for message received in the form of Q and RQG. See, what it is actually sending along with that particular message is it is piggybacking SPG. So the source sequence number, okay. So the message, what is the last message like it has actually sent, okay. What is the current sequence number of the message which it is actually being sent. Okay, and then like all the acknowledgements, okay, acknowledgement values for all the processes from which like it has actually received these particular messages. So basically like for if this is P1, so for P2 it will have this sort of R P2G, and P3 R P3G, okay, and everything. So for every other process like it will send that. So these piggyback message values actually allow this sort of recipient, whoever actually has received this particular message along with the message, can actually learn like about the message they have not yet received. For example, if process P1 basically says like it is sending the third message, so that means like its SPG is the third message, 3, okay, and then like it will basically say like I received from process P2 two messages. Now, if you send this message, everyone who is in the multicast group actually knows like this P1 actually has received two messages from P2. And if somebody has not received two messages from P2, then there is an issue. Okay, that means like he may actually miss that particular message. And also like anyhow, since like you are actually getting this SPG value, okay, so you already know like, so this process P1 is sending the third message. Okay, so these can be actually used by the other processors within that particular group. Of course, like once you basically multicast that one, okay, so you will actually increase this SPG value by 1, okay, because like you have sent one more value, and that's what like you are actually multicasting, okay, with the piggyback. Now at the receiving side, a process which actually receives this particular message, okay, which is targeted for that particular group G, and it has a value of S, okay, so it's a source value, okay, source sequence number, okay, from that particular key. Then what it will do is like it will basically try to get its RPG. So basically like what is the last sequence number, okay, what is the last message and its sequence number which you have received from P, and you will basically check the S value which you have received in the current message, okay. If this S is equal to whatever the previous value plus 1, then great, you have not lost any message, so you will immediately R deliver the message and you will actually increment this sort of RPG value by 1, okay. And if S is actually less than RPG, okay, that means like you already received a higher sequence number, okay, for that particular process message, and then like you are receiving a new message that actually states like you are actually getting a duplicate message, okay. The message is already received and then like you have moved ahead and then like you are receiving a message which is from some previous time, you will basically discard that particular message. The third case is very interesting. If the S value is actually greater than RPG plus 1, so then what it means? You have actually lost some message, okay, in the middle. Similarly, like if you have received this sort of acknowledgement like Q comma R, okay, so that means like the process P which actually has sent the message, it's receiving sequence number, okay, from particular process Q, okay, and if this R value is actually less than what the current Q process actually has received, so then that means the process P actually received lesser number of messages than what the other processes within that particular multicast group has actually received. So with these conditions, like then basically like first point is like then it has actually missed messages and requests them with negative acknowledgements. See, if S is greater than this sort of RPG plus 1, so that means like this receiving process actually has missed some messages, so it will basically send this sort of negative acknowledgements to basically get the previous message as well. This thing you can actually achieve in two ways. One thing is like you can actually send it directly, okay, this negative acknowledgement to this sort of multicaster itself. Alternatively, you can basically ask from any process, okay, which actually has that one. Of course, if you are doing this one, then you will put this sort of new message in this sort of holdback queue for later delivery. Let me try to show you with an example. Assume like there are process P1, P2, P3, and you can actually maintain this sort of vectors. For the process P1, like the first value is the S value, okay. and the other ones are the R values, because like S is the one which is the message sequence number which it has actually sent. For P1 this is the S, for P2 the second value is the S, for P3 third value is the S. For other things it is like R value. So this basically shows like received sequence number of the received messages from process P2. So the second value. The third value is from process P3. The same thing appears for everything. Now assume like at certain point like P2 has actually delivered, okay, it is multicasting a message. Now assume like if P1 actually received that particular message in time. So what you are doing is like once you have multicast that one, its S value you actually increase. So I have already delivered multicast one message to this particular group 0 1 0. Now when you are sending that particular message, when you are multicasting it, what you are doing, you are actually sending information. The message has the sender information, so that means like it is coming from process P2, and you have piggybacked all the values, so the both all the S and R values, in this case like R at P2, okay, so from P1 is 0, from P3 is also 0, but its S value is 1. Now if this message is actually, and the message is actually M1, if this message is actually received at P1, it basically will check, okay, so the message is actually coming from 2, and then like it will actually check its S value. The S value in this case it is 1. Originally the S value, I mean like the R value there, okay, R P2 for that particular group is 0. That means like it is 0 plus 1, which is actually 1. So that means like this is the latest message it is receiving. So then basically like it will receive the message, it will update its values, that its S value is still 0, it has not sent anything. Its received value from R P2 G is 1, okay, R P3 G is still 0. Okay, similarly like later after some more time, like if P2 is basically sending the message, okay, so it will receive again like with 2, and now that it has added one more message, so now its value basically becomes 2, and you will basically get this 0 because like it has not received any message from P3, and then like you are sending M2 to this one, and once you will basically come here you will check, okay, so the S value, so the R value, okay, whatever the S value which you are receiving from this one, S P2G, okay, is actually R P2G plus 1. So basically like it is fine, so it will also like R deliver that particular message, and then like it will update its own vectors. But now think about a tricky situation at P3. Assume like, because like you can actually miss the message and the reliable multicast like it is sending it several times. Assume like process P2, from process P2 the message M2 is received first, but then like because of the piggybacking, okay, so all the acknowledgements, the message it is actually receiving is, it is coming from process 2, and you have this sort of 0, okay, and S value SP2 G is actually 2 here, okay, and then like M2 is actually delivered. When this particular message basically comes into the process 3, then it will actually check. So the SP2G, okay, with which like the message is actually received is actually 2, whereas like RP2G at P3 is actually 0. So this is more than 2. So that means like you will not basically reliable R multicast this message, rather you will put it in the holdback queue, and later like you will actually at certain point like you will receive this M1, okay, and M1 perfectly matches with it, and then like it will R multicast that particular message, and then like after that one like the message which is in the holdback will satisfy its constraints, and then like it is also R multicast, and after that like the vector basically changes. This is about if a message is lost. Similarly, like the other conditions also can be thought about. Say for example, even before this particular message is sent, like if you send another message from P1, okay, and you basically try to send it to multicast it, then assume like it is received into P3 first. Then its piggyback message will basically say like I already received from P1, okay, from P2 a message, and then like it will basically come here. Then you will actually check like P1 actually has received a message from P2 already, and I have not received that one. And then like it can basically send this sort of negative acknowledgement to P2 to send that particular message. Of course, like I have not represented that in this figure, but then like that can also happen. Regarding the reference are concerned, so the material is actually taken from chapter 15th of this distributed system concepts and design by Coloris et al. Thank you very much for your attention.